we want to introduce line integrals. Now the idea here is I have a path rather than a region or a surface or even a volume, and I want to integrate along this path some function f of xy. Now f of xy could represent density, it could represent force, and overall I want to integrate along a path, so the type of setup is going to be a bit different. So there's three basic forms a line integral can take on. I'm going to integrate f of xy over the path c, this is the notation, with respect to x. I'm going to integrate f of xy with respect to y, or I can integrate f of xy with respect to the arc length parameter. Now in each case we have a single integral with multiple variables, so this will require parameterization. So I want to go through each of the three of these so you can see what they look like. Let's consider the following problem. I have the quarter circle, x squared plus y squared equals 36 in the first quadrant, going from 6, 0 to 0, 6. So in this situation here, the usual parameterization for a circle would be to choose x equals 6 cos t, y equals 6 sine t, and then t would range from 0 to pi over 2. So in this scenario, I can integrate with respect to x, so my dx would be negative 6 sine t dt. I can integrate with respect to y, so my dy would be 6 cos t dt, or I can integrate with respect to the arc length parameter, which would be the sum of the squares, under the root dt, and we recognize that would just be 6 dt. So depending on which one I choose, the integration is going to look very different in the setup. So let's look at the first possible case. When I use my parameterization, I replace x with 6 cos t, y with 6 sine t, and then dx with negative 6 sine t dt, and we're integrating from 0 to pi over 2. Well, this gives us negative 216, and we get sine squared t cos t dt. If I think of this as a u substitution, if my u is sine t, then my du is cos t dt, so this is already in a perfect form of u squared du. So my antiderivative 1/3 u cubed would give us negative 72 times sine cubed from 0 to pi over 2, which would just be negative 72. Now the second example, we'll integrate with respect to y. So again, I'll get 6 cos t times 6 sine t, but then the dy this time would be 6 cos t dt, again integrating from 0 to pi over 2. This will give us 216, and this time we'll write it as cos squared t times sine t dt. So once again, if I let my u be the cosine function, then the du would be the negative of the sine function. So again, I will have something of the form u squared du, so the antiderivative being 1/3 u cubed. So I would get negative 72 times the cube of the cosine from 0 to pi over 2. Well, that will be 0 minus 1, so this will give us positive 72 as an answer. Now, the third case, we're going to integrate with respect to the arc length parameter. So here we will get, again, 6 times the cosine of t, 6 times the sine of t, and then 6 dt, 0 to pi over 2, which would be 216. And we'll write this as sine t cos t dt. So again, if I choose my u to be the sine function, then du is cos, and then I would be integrating u du, so the antiderivative being 1/2 u squared. I will get 108 sine squared, and this will just be 108. So you see the three different forms produce three different numerical answers, which is to be expected. So let's continue now. We're going to look at the most common type of line integral, one that involves both a dx and a dy at the same time. So we definitely have to parameterize, but once we choose our parameterization, we will have a function of one variable, and the integration is usually fairly simple. Now, we want to go along the following path, x equal cube root of y, from 1, 1 to 327. So I can either choose x to be my t and then y to be t to the 1/3. That sounds a little daunting, so why don't instead I reach and change this to y equals x cubed. If I do that, then I would choose x to be t, y to be t cubed, dx is then 1 dt, dy is then 3t squared dt, and since we chose x to be t, it's clear to see that t will range from 1 to 3. So what we're going to do is rewrite this integral by replacing x with t, y with t cubed, and also replacing the dx and the dy. So we want to do this part slowly. So we'll have the integral from 1 to 3 of, so we'll have t squared times t cubed squared, dx, and just think of this as 1 dx, plus 2 times t cubed times t cubed, and then the dy was 3t squared, and then the whole thing was dt. You don't really need to write dt twice. So as I simplify this, I'll notice this piece here is t to the 8th power. This piece here also has a t to the 8th power. That would be a 6t to the 8th. So this reduces fairly nicely. 1 to 3 of 7t to the 8th power dt. The antiderivative being 7 over 9 t to the 9th from 1 to 3, and then simply getting out your calculator or doing it in your head, it doesn't matter. So 15,309. Now this would be a very typical type of problem. So the question might be, find the work done along this path given the following function, and then we get to here. Now there are several more examples online on Canvas if you want to look these over.